Hello all. So today we're going to talk about the second topic in volume, and this is finding the volume of a solid that is rotating about an axis, but this time we're going to be using washers. And so I have a picture of a few different washers here just to remind you of what washers look like, and there's all different thicknesses and things like that, and so you kind of have that picture in your head as we move through this. The washer method is used when we are graphing two functions. So you can see in this picture here, we have this shaded region right here that is bounded by two different functions. And when you take that and rotate it about the x-axis, you can see that the entire thing isn't touching the x-axis. So as you rotate it around, you're going to have this hole, and therefore forming a washer shape. Okay, when we do this formula, there's two different radii that are really formed with the washer. And so if you look here, you have one, both start at the very center, and you have one that goes all the way to the outside edge, and that we would call capital R. Okay, that's going to be our one radius. The other radius is just from the center then to the inside edge of our washer, and that's our lowercase r. And as we walk through this formula, we're going to be using that capital R and the lowercase r to develop our formula. So it's important that we understand which one we're talking about. The other thing we want to make sure we do is always draw in our radius, both of our radius, okay, perpendicular to axis of rotation. So when we do this, if we have a horizontal axis of rotation, we're going to be drawing our radii up and down. If we have a vertical axis of rotation, like the y-axis or another x equals line, then we're going to be drawing our radii left to right. Okay, so what is the formula then for the volume of this shaded region rotated about the axes? We're going to go ahead and say the volume is equal to pi times the integral from a to b, and I guess our drawing needs an a and a b here. This would be our a, and this would be our b. So again, they're intersection points, okay? So the integral from a to b of capital R squared minus lowercase r squared dx. So that is the formula that we're going to be working with. All right, let's go ahead and get started and try some. Okay, so as we look at our first question here, the directions say, let region S be the region bounded by the functions given. Find the volume of the solid formed when S is rotated around the indicated axis. Okay, so we are going to go ahead and graph these two functions, f of x and g of x, and you can see that our first axis of rotation is the x-axis. We're actually going to work with these same two functions, the square root of x and x squared, for the next several problems. That way keeping the same picture, but we're going to change our axis of rotation. All right, so let's go ahead and get a sketch here. So clearly we have the x and y axis, and I'm going to indicate that this is our axis of rotation, okay? And so we can go ahead and graph y equals the square root of x. So we know that has the point 0, 0 and the point 1, 1. So I'll just kind of graph that in. Okay, and then we'll also graph in y equals x squared, which also has 0, 0 and 1, 1 as an intersection point. Okay, so we have those two functions graphed in. And of course, this region that is bounded between them, that's enclosed between them, is our region S. All right, so we have that picture drawn. Now what we need to do is get our radii. Okay, so we are looking now for a picture of the radius, and when we draw in our rectangle, we're going to draw it in perpendicular to the axis of rotation. So there it is. And we have two different radii. Imagine taking this yellow shaded region and rotating it around. Okay, you can see how you're going to have two different radii. You're going to have the big one that goes all the way from the axis to the top curve. Okay, that's going to be our first radii. So we're going to go ahead and label all of this with a capital R. Okay, and then of course we have this smaller radius. That's where our hole is going to be, and we're going to label that with a lowercase r. All right, so now that we have that, we're ready to go ahead and start writing out our formula for the volume. Okay, so in this case, we're going to go ahead and say the volume is equal to pi times the integral. Okay, well, it looks like I need my bounds. And we kind of talked through, we know what this point is, but if not, we could have always taken and set these two functions equal to each other. Square root of x is equal to x squared. Okay, I just used some common sense, and I know that square root of 1 is 1, and I know that 1 squared is 1. And so that's how I knew, and of course the square root of 0 is 0, and 0 squared is 0. So that's how I knew those two intersection points. But if that didn't happen, of course, we could set them equal to each other. In order to solve this, we'd square both sides. So that would be x is equal to x to the fourth. When I brought that over, I would have 0 is equal to x to the fourth minus x. Factor out an x, and I'd have x cubed minus 1. So then I get x equals 0, and x cubed equals 1, so x would equal 1. So there's my 2 points, and that gives me my A and my B. Okay, so that's my 0 to 1. Those are my bounds that I'm working within. Okay, and of course, this is all in terms of x because I'm rotating around the x-axis. All right, so now I need my capital R squared minus my lowercase r squared. So remember, whenever we're talking about finding the length of that rectangle, okay, we're talking about upper minus lower for when we're in terms of x. So the upper curve here is the square root of x, and so I would say the square root of x minus my lower is 0. That's the x-axis, squared. Okay, so then minus your little r squared. So your little r you can see is the green curve, okay? It's bounded by the green curve in the x-axis. So the green curve, of course, is our g of x, and that's our x squared. So we would say x squared minus 0 squared. And then that's all dx. Okay, I should really have labels on this. This should be my G, and this is my F. All right, so now we're going to go ahead and just kind of simplify this and move through this problem. So the integral from 0 to 1 of the square root of x squared is just going to be x minus x squared squared is going to be x to the fourth, and then dx. All right, so we're ready to go ahead and integrate this. So I'm just going to scooch that up a little bit. All right, so volume is going to equal pi times. All right, let's do the integral of x would be x squared over 2 minus x to the fifth over 5 from 0 to 1. So volume equals pi times, let's see, it's going to be 1/2 minus 1/5, and then, of course, minus 0. So we end up here with 1/2 is the same as 5/10. 1/5 is the same as 2/10. So we end up with 3 pi over 10 as the volume of that solid being rotated about the x-axis. Okay, so number 2 is f of x is the square root of x, g of x is x squared. So the same two functions, f and g, but this time we're rotating about the line y equals 2. So I went ahead and made a sketch, and I asked that you, again, I know it's annoying, but I want you to make a second sketch so that we can get everything labeled in there. And this time we definitely need to draw in that new axis of rotation, which is y equals 2. So I'm going to go ahead and graph in the line y equals 2. Okay, so now I'm going to have to draw in, again, those lines representing my two radii. So we want it to be perpendicular, the radii to be drawn perpendicular to our axis of rotation. So this time we're going to start from the green curve, from my G curve, and go all the way up perpendicular with that axis of rotation. So this time my big R is, of course, this whole piece, and the lowercase r would be from here just to the red curve. Okay, so there's my two radii. So this time I have the big R and the little r, and you can, again, if you visualize, taking that and rotating it about the line y equals 2, you can visualize how that's going to happen. Okay, so this time no piece of it is actually touching the line, the horizontal line y equals 2, and that's all right. You're literally taking it and spinning it in the air around that piece. And so what's going to happen is you're going to have this piece that's going to be rotated around. You're going to end up forming a donut kind of shape curve. All right, so we're ready to go ahead and use our formula to fill in our pieces. We, of course, know our bounds because we figured those out last time, and we know that we are bounded here by 0 and 1. Okay, so we're going to say volume is equal to pi times the integral from 0 to 1 of, now, our capital R, remember it's always upper minus lower. So our capital R here would be from 2 minus all the way down to the g curve. So this time it's 2 minus x squared quantity squared. So that's your capital R squared minus my lowercase r squared. Okay, well again that starts with 2, but now you're subtracting the square root of x quantity squared dx. Okay, so make sure that that sinks in for you. It's always upper minus lower. And so when you have an axis other than the x-axis, you're going to have a value to that. And so it can either be positive or negative. And if it's negative, we're going to look at ones like that in a minute. All right, so you always want to do your upper curve minus your lower curve to find your length of your radii. Okay. All right, the point of this video is not to go through and teach you how to do the integral and evaluate this. We're really just trying to teach you how to do the volume. And so I want to get in as many examples as I can. So we're not going to go through this. This would be actually quite a mess, and it would be quite involved because you're going to have to FOIL here. You'd have to write this twice and FOIL it, write this twice and FOIL it, and then combine like terms, and then do the integrating, and then plug in your bounds. It just gets into quite this long problem. So I'm sure you're all thankful. We're going to stop here. I just wanted to write out the formula. And oftentimes, actually on the exam, there's times when you're asked to do that. It'll say write but do not integrate, or write but do not solve. And it'll just want you to be able to write it out. So this is kind of practice for one of those type. All right, let's move on. In the next two, we're going to do, again, using the same F and G, but this time we're going to be rotating about vertical axes. Okay, as I said, we have the same graph, so take a second to go ahead and sketch that. Notice that I put my axis of rotation here. I put the symbol of rotation around the y-axis down here, okay? But everything else is the same. So, couple things to keep in mind when we're rotating about the y-axis or any vertical axis. When we draw on our radii, remember it's always got to be perpendicular to the axis of rotation, so we're going to be drawing horizontal radii this time. The other thing you want to keep in mind is that everything has to be in terms of y. That includes your bounds and your functions. Okay, so we're going to have to do some transforming of these functions in order to make that happen. All right, so let's do that first just to get that kind of out of the way. Okay, so if we start with the first curve, y equals square root of x. Remember, we want these in terms of y, so that means we need to solve for x. All right, so that would mean in this case, I'm just going to square both sides. So one step and I'm done. X equals y squared. So I'm going to kind of stick that by this graph. That was my F. So I'm going to write this as x equals y squared. Okay, now the next one is y equals x squared. Again, I'm solving for x in terms of y. And so again, this time I'm taking the square root of both sides in order to get rid of. So I'd have the square root of y is equal to x. And again, let's write that right by this curve so we know what it's called. So x equals the square root of y. All right, so those are my two curves in terms of y, and now we need our bounds in terms of y. So remember that this point here was 1, 1, and this point here is 0, 0. So actually our bounds don't change. It's just we're looking at those as up and down as opposed to left and right. All right, next thing I want to do is go ahead and get that radii drawn in. And so we are drawing in a horizontal radius perpendicular to the axis of rotation. So in this case, this long one would be my capital R, and this short one would be my lowercase r. Okay, so again, same formula, it's just that we have everything in terms of y. So as I create this formula, I'd say volume is equal to pi times the integral from 0 to 1. Okay, now this time, capital R squared, it's always capital R squared minus lowercase r squared. So my capital R squared for in terms of y problems, when we're rotating, it's going to be right minus left. Okay, so keep that in mind. So when we are figuring out our radius, it's right minus left. So in this case, the right curve would be my green curve, my G curve, which I renamed as the square root of y. So I'm going to go ahead and say it'd be the square root of y, the square root of y minus 0, because of course the y-axis has an equation x equals 0, and then that's squared, minus lowercase r is the red curve, the f curve, which of course I've renamed as x equals y squared. So y squared minus 0 quantity squared dy. Okay, so this actually looks very familiar to what we had done earlier when we rotated about the x-axis. And again, I'm going to stop here. We're not going to go through and solve it. I just wanted to set it up for you so you can kind of visualize it and see it. We're going to do one more problem like this, and then we're going to do a couple on our calculators. Okay, so our last example of this type, again, we have that same basic graph that we've seen, and I went ahead, and because I know that I'm revolving it around an axis that is a vertical axis, I went ahead and wrote the equations in terms of y, okay, just like we had figured out on the last one. So those are all set. All right, now this is drawn pretty grossly out of scale because this is supposed to be the line, the vertical line, x equals -4. Clearly that's not -4 if this is 1, but we get the idea, just so that we have a visual image of what's going on. Okay, so again, think about you rotating this yellow shape around this axis. So this axis is permanent, okay? It is stationary. And what's happening is you're spinning this around. So it's coming out at you, around, back behind that line, and back to where it is. So you can imagine it's spinning around a pole, okay? All right, so we need to go ahead and draw in our two different radii. And again, the radii are drawn perpendicular to the axis of rotation. So I'm going to draw in this very long rectangular slice, okay? And that's going to represent my big R. So all of this is big R. And in this case, then, from here to here is my lowercase r. All right, so now we're ready to go to the formula. And of course, we know our bounds, so we can get those in there. Our bounds are still 0 to 1. Okay, so this is the picture that's going to help us to create our formula. Okay, so our formula is volume equals pi times the integral from 0 to 1. And okay, we're talking again, capital R squared minus lowercase r squared. And again, it's right minus left. So in this case, where it's not centered at an axis, when it's at an equation x equals -4, we definitely have to keep in mind right minus left. So in this case, capital R, okay, the big longer one, starts at the green curve, which in terms of y is the square root of y minus -4, which is really plus 4 squared. Minus, now you need your lowercase r, okay? So that's your smaller radius, and that starts at the red curve on the right-hand side, and then it's minus -4 again. So I would say that is y squared minus -4, so plus 4 quantity squared, and then dy. And again, if you went ahead and you'd have to FOIL both of those, you'd have to combine like terms, then integrate, and then plug in your bounds, and you'd finally have an answer. But what I wanted to work through is just setting up that formula and understanding this concept of figuring out the big R versus the smaller r. All right, we're going to go ahead and do 2 problems on the calculator, and then we'll be finished for the night. Okay, so taking a look at this first example with calculator, these are actual AP questions, the next 2 ones that we're going to do. So let f and g be the functions given by, and give you the equations for f and g. Let R be the shaded region in the first quadrant enclosed by the graphs f and g as shown in the figure above. Find the volume of the solid generated when R is revolved about the x-axis. Okay, so first thing I want to do is draw in my radii. Draw in that rectangle perpendicular to the axis of rotation. Okay, so not exactly perpendicular there, but you get the idea. Okay, so, and of course, from here to here would be my capital R, and from here to here would be my lowercase r. Okay, so looking at this, we have a lot of information. We know what the equation for f of x and for g of x is. Okay, we can then create expressions for capital R and for lower r. But what we don't know are our bounds. We don't know this point of intersection over here. Whoops. What the value is of this point right here. And so what we need to do is calculate this point of intersection using our calculator. Okay, now be careful. One of your functions is a trig function, so make sure you're in radian mode. All right. You can tell that you're in the first quadrant. They told you it's a first quadrant enclosed, and so you want to make sure that you are setting your window so you're only looking at the first quadrant and find that point of intersection. I'm going to ask you to go ahead and pause your video, find that point of intersection on your calculator. Remember, working with your calculator, those skills are super important that you are able to do that, so you have to practice that on your own. Get that point of intersection, come back to me and see if we agree. Okay, so I found the intersection point to be this 1.1356 blah, blah, blah. All right, so hopefully you remember to store that into your calculator. I stored it as alpha b. Okay, if you haven't, please go ahead and do that now to make sure it gets stored in as b. All right, so now I'm going to go ahead and write the formula for the volume. So if you're feeling confident, which I hope you are, I want you to go ahead and pause it and write your own formula. And then come back and make sure it's okay. Then we're going to enter it in the calculator and we'll be done with this problem. Okay, so check out the formula that I wrote and hopefully it's the same as you did. Now we're going to just enter that in our calculator and we'll come up with an answer. So pause the video again, enter that into your calculator, and let's see if we get the same answer. Okay, so compare your answer with mine and hopefully we both got the same volume. If not, check what you typed in your calculator. You want to make sure that you are putting parentheses around each of these terms before hitting squared, minus, and then another parenthesis squared. And it should, in your calculator, the way it works out is you will have another set of big parentheses around the whole thing. So please make sure that you are entering in that all correctly and that you got the same answer as I did. And we're going to try one last problem. Okay, so this is part A, B, and C of a actual AP free response question. So you can see here that we have f and g, and f of x is 1/4 plus sine pi x, and g of x is 4 to the negative x. And R is the shaded region in the first quadrant enclosed by the y-axis and the graphs of f and g, and S be the shaded region in the first quadrant enclosed by f and g. Okay, so they ask us to do three different things. Find the area of R, area of S, and the volume of the solid generated when S is revolved around the horizontal line y equals -1. All right, so let's, for a second, just remind ourselves about area. Okay, it's been a couple of classes since we did area. The area formula, of course, is base times height. And so if you remember here, we draw in a rectangle in the region. So if I look at region R and draw in a rectangle, my base is the dx, okay? And then the height is the upper minus lower curve. And that's all it is, the integral from, in this case, it'll be 0 to, we are going to have to find this first intersection point, we'll call it A, and then of upper minus lower dx. All right, and then when we move on to S, we'll draw in another rectangle here. And same thing, my base is dx. My upper this time is f of x and lower is g of x. And again, our bounds are now from A to, in this case, B. So we're going to have to find out what that other intersection point is. So what I'd like you to do right now, pause the video. Get this graph into your graphing calculator. You're looking again in the first quadrant. Find your A and your B, write them down. Okay, calculate their intersection points, write them down. Store them into A and B. Okay, then we're going to go ahead and I'd like you to write the formulas that you would use to find the area of R and the area of S. And go ahead and get those into your calculator and calculate those. Okay, so that's a lot of things you're doing. Finding A and B, writing down the formulas for the area for R and S, and then calculating them, and then come back and we'll see if we agree. Okay, so take a look at your answers and compare them with mine. Okay, so if you look at the area of R, okay, so the area is from 0 to A, the integral from 0 to A, which I found my A and my B up here. A was this big long 0.178218, blah, blah, blah. B happened to be a whole number 1. Okay, so the integral from 0 to a of upper minus lower. So for r, the upper curve is g of x, and the lower curve is f of x. So it's g of x minus f of x, and then dx is 0.065. All right, for the area of S, the area is, again, the integral from a to 1, okay, or you could say a to b, of, in this case, it's f of x, your upper curve is f of x, minus your lower curve is g of x, dx, equals 0.410. So there's no squareds with area. That's the most important thing to remember, okay? Area, there's no pi's and there's no squareds. You're just doing upper minus lower, and that's as simple as that. All right, now, letter C is starting to talk about a new line that's graphed in, okay? So we have to graph in a line here, y equals -1. So I am obviously, again, not drawing it to scale, but there is my line y equals -1. Okay, so if I were to continue on that axis. So I'm going to rotate S, revolve it around that horizontal line. So what does that mean I need to do? That means I need to draw in my radii. So I'm going to go ahead and draw in all the way through S down perpendicular with the line that I'm revolving around. And so that whole piece is my capital R, and this piece here is my little r. Okay, and so now I'm talking about volume. And so let's go ahead and get the formula written out. Volume equals pi times the integral from a to b, or you could say a to 1, of, okay, now we need our big R, which is upper minus lower, so in this case f of x, and you can write it this way, you don't have to replace in, so f of x minus -1 squared, or you could change that to +1, okay, minus, now your little r is the lower curve, which is your g of x, minus -1 quantity squared. Again, you could change that to +1. And then this is all times dx. Okay, so go ahead and enter that into your calculator and see if we get the same answer for that one. Okay, that was a lot to type into your calculator. Hopefully you did it nice and carefully, and you ended up with the same answer I did, that the volume is 4.559. Okay, thanks a lot, guys. I really hope that you are taking good notes here, that you have got this down, that you're remembering the formula. Okay, if I were to summarize, you want to make sure that you understand that the for volume, when you are talking about washer, okay, and that's when you have two functions that are overlapping and forming a region that you are then revolving, is the integral from a to b of capital R squared minus lowercase r squared dx. So please make sure that you have that memorized and that you know what capital R and lowercase r stand for. All right, thanks a lot, and I will see you next time.